Hello, I'm Mrs. Edwards, and we're back. We're going to talk about power functions today. We're going to start with identifying power functions. So we'll look at several equations and decide if they actually are a power function. And then we'll go from the power functions written in words and translating those into equations and back and forth. Okay, so let's start with, what is a power function? It is an equation that is written in the form f of x equals k times x to the power of a. K is a constant, and so is a. And as long as a and k are not equal to 0, we've got ourselves a power function. Here we have seven different equations, and we want to know, are they power functions? And if they are power functions, we want to be able to identify the power and the constant. So here's a quick reminder of what a power function should look like. Next, in the directions, we see that c, g, k, and pi all represent constants. In other words, those symbols will not be replaced with a whole bunch of different numbers. They represent a single number that does not change, that is constant. So let's start by just running through the equations and identifying the constants that we already know. In that first equation here, c is a constant. The next equation, both g and k, then c. The following one, g. Then we have k. We have pi. All right, then we also have some other constants that are just sitting there that we didn't need this special set of directions at the top. Any number is a constant. So we also have in the fourth equation down, the 1/7, that is a constant. And then the very last equation, the number -6, that's a constant. All right, so we've highlighted in blue all of the constants. We're trying to continue to compare back and forth. Does it look like f of x equals k times x to the a, where k is the constant? Next, let's take a look at just the output. You know, you input an x value and you get an output of f of x. Well, in this case here, I input an x and I get an output of b of x. So here's all of our outputs. Everything there on the left-hand side, that's like our y coordinate. So far, looking back and forth, making that comparison, they're looking like power functions. Okay, next, we want to see that x is the base and a is the power. That's our exponent there. So let's just identify the variable. Now in this one, it's x. So the base is x. So x, the base is x. This one, the input variable is t. So the base should be t. Here, we're inputting x, and so the base is x. This one is like kind of y equals. It's just that g represents the y. So our base in this one happens to be x. We know it is a variable because it wasn't in this list up here. Okay, this one here, we input x, and what? Look at the location of x. X is not the base. X is in the exponent. This one here is an exponential function. You can tell exponential functions because the variable is located in the exponent. So we know right now that is not a power function. Okay, moving on. We have the g equals, g is like our y coordinate, and then m is not in our list up here, c, g, k, pi. So m is a variable. And then in f of x, our input is x, but on this side we don't see an x. We don't see it, but technically it's there. That would be like x to the power of 0, because anything to the 0 power is 1, and we'd have -6 times 1, which gets us back to -6. All right, so in purple, we've just emphasized what the variable in the problem is. Next, let's focus on the power. In the first one, the power is 3. I'm highlighting those in yellow. In the next one, the power is also 3. The third one, the power is 3 again. And the fourth one, 3. Okay, our f of x equals k times 2 to the x is not a power function, so that's an irrelevant question. Then we get down here to g equals pi m to the third. We have to be a little more creative because we've got to force it to look like that. So if we want it to look like this, the x needs to be up there in the numerator. Our variable in this one is m, so we want m to be up in the numerator. I use the, I made up a saying that's cross the line to change the sign. If you want to cross the line, you want m to be in the numerator, you can do that by changing the sign on the exponent. So we're going to move m to the top there. So we have m to the power of negative 3. Now this definitely looks like our power function, and the negative 3 is the power. And that last one, we already wrote x to the 0 power to emphasize our variable, and then inadvertently we also got the power. So that one has a power of 0. Next, for the constants. If we want the constant of variation, we've already highlighted all the constants in blue, and it's the number sitting in front of x. So in this first one, the constant of variation would be c. This one would be gk. This one would be c. The constant of variation, you might say 1/7 g, but if you multiply 1/7 times g, that's like taking 1/7 times g over 1, you get g over 7. So you might see 1/7 g listed as the constant or g over 7. Okay, then the next one, the constant of variation is k. Here the constant is pi. And then here the constant is negative 6. Really quick, back to this algebraic manipulation. To force this to look like a power function, we went and changed the pi over m to the third to pi m to the negative 3. Let's go over quickly one other algebraic manipulation that you're going to need to be able to rewrite something so it looks like a power function, where x is the base and then we have an exponent. This is just a reminder of how you go from root form to exponential form. I have the bth root of x to the power of a. That is equivalent to x to the a over b. The way that I remember it is a is on the inside of the root symbol and b is on the outside. If you were to flip a shirt inside out, then a inside out. And so in the numerator, inside out. That just helps me to remember the order. We're going to be translating some sentences into equations. So how does k times look in words? There are 3 ways that you can see. One is k varies. Another is k varies directly. And a third is k is directly proportional to. If you see any one of these 3 statements, that is equivalent to k times. So when I read a sentence and I see k varies, my brain translates it to k times. Or k varies directly. I don't see that. I see k times. Or k is directly proportional to. Nope, that means k times. Another way that you might see it is k divided by. Now technically, once we get it to a power function, we're going to have to cross the line and change the sign on the exponent to make it look like a power function. And we'll see that in action in just a second. But the words that translate to k divided by is k varies inversely, or k is inversely proportional to. If you see either one of these statements, you can just replace those words with k divided by. Here we have a story problem that's going to allow us to put a couple of those things we talked about into action. All right, so here's the scenario. The empirical evidence and the laws of physics. It has been found that the period of time t for a full swing of a pendulum varies as the square root of a pendulum's length L, provided that the swing is small relative to the length of the pendulum. Model this relationship as a power function. Okay, model it as a power function means to translate this into an equation that looks like f of x equals k times x to the power of a. Here I've highlighted the important words in this situation. The period of time t, so that's t, then the word varies translates to k times. The square root of the pendulum's length L, well, that's just the square root of L. Here we have our equation, period of time t equals k times, because varies, and then the square root of the pendulum's length L. Now we have translated this, but we want to make it specifically look like a power function. So we need to emphasize there's a base to an exponent. Here we're going to use that move. The L is to the first power, and this is a square root. We just don't see the 1 and the 2, but we know they're there. We can rewrite that. It's going to be to the power of, inside out, 1/2. So we have t equals k times L to the power of 1/2. Now we have modeled this information using a power function. Notice that subtlety. You cannot leave it as the square root of L. It would then be a square root function. You've got to make it look like k times x to the a, so we can clearly see the constant is k and the exponent is 1/2. Here we're going to take several power function equations and rewrite a statement that represents them. But you should be able to go back and forth between the two of these. The first one that we're going to take a look at is circumference equals 2 pi r. You want to identify the constant there because you don't want to say 2 pi. You want to use one of those statements that represents k times. Really just seeing several examples is going to help you to understand this. So notice as I'm writing this, the circumference of a circle varies directly as its radius. I didn't say 2 pi times, I didn't say k times. Remember the words k times can be interchanged with varies directly. That's not the only way that you could say it. You could also just say varies, or you could say is directly proportional to. So again, 2 pi, that's like k times. So rather than saying 2 pi, you can say varies directly, or is directly proportional to. I want to put all three there because I know sometimes when you check the back of the book, you check with Bob, and it has written it slightly differently, you start to doubt yourself. And you compare and you're looking for a pattern. It doesn't matter which one of these three that you write. All of them are just fine. They're interchangeable. Let's look at another one that's like that. Here we have a equals pi times r squared. But if we want to write the statement as a power function, that pi is like pi times. That's like k times. So rather than saying k times, rather than saying pi times, we're going to replace those words with varies directly, or is directly proportional to. So here we go. The area of a circle varies directly as the square of its radius. Now someone else might have said varies rather than varies directly, and another person may have said is directly proportional to. All three of these statements would be just fine. Now let's take a look at one where we see divided by. Notice we have k divided by. Now in just a moment ago, I reminded you that k divided by can be replaced with the words varies inversely, or is inversely proportional to. So what we want to say here is the force of gravity on an object is inversely proportional to the square of the distance from the object to the center of the earth. All right, another way that I could have said that, instead of inversely proportional, I could say varies inversely. Notice I'm not saying k divided by, I'm going to say varies inversely or inversely proportional rather than k divided by. Here's another one like that with Boyle's law. Just identifying those pieces. Okay, so instead of saying k divided by, I'm going to either say varies inversely or inversely proportional. So here's a sentence. The volume of an enclosed gas is inversely proportional to the applied pressure. So notice inversely proportional rather than k divided by. Another person could have said the volume of the enclosed glass varies inversely to the applied pressure. That would have worked as well. Let's now just focus on writing it as a power function. Not all of these look like a power function. This first one does already look like a power function. The power there and the constant of variation, the power is 1 and the constant of variation is 2 pi. The next one already looks like a power function as well. So the pi is the constant of variation and the 2 is our power. The next one does not quite look like a power function. We need to rewrite it in the form k times x to the power of. So what we're going to do is cross the line to change the sign. I'm moving d squared to the numerator by making that d to the power of -2. Now we can see that k is the constant of variation and -2 is the power. Similarly, in Boyle's law, that equation sitting there does not look like a power function, so we need to rewrite it to make it look like a power function. It's currently divided by p, so it's p to the first power in the denominator. So we're going to move it to the numerator by changing the sign on the exponent. Cross the line to change the sign of the exponent. So we actually have k times p to the -1, and then k is going to be the constant of variation, and the power is -1. One more time, you should be able to go back and forth. If you read this statement over here, you would want to write v equals k p to the -2. Or if you read one of these statements here, you would write f equals k d to the -2. Because writing something as a power function, you cannot write it as, for example, force equals k divided by d squared. You've got to make it look exactly like that.